Three-phase motors typically use laminated silicon steel cores, which reduce energy loss from eddy currents, improving efficiency. The core laminations are created by stamping thin sheets of silicon steel, stacked to form the stator and rotor cores. The stator core is assembled by stacking and pressing these lamination sheets to create a stable, compact core. Copper or aluminum wire is wound around the stator slots. In three-phase motors, 3 separate windings are arranged at 120-degree angles. Each winding is insulated to prevent short circuits, often using varnish, tape, or an epoxy coating for thermal resistance. High-precision winding machines are used to ensure consistent wire placement, reducing human error and enhancing performance. The rotor core, like the stator, is created by stacking laminated steel sheets to reduce losses and improve magnetic performance. In induction motors, aluminum or copper is cast into the rotor slots to form conductive bars that create the magnetic field. A steel shaft is inserted through the rotor core, allowing it to spin within the stator field and create rotational motion. Bearings are installed at each end of the shaft to ensure smooth rotation, reduce friction, and support the rotor assembly. The rotor assembly is balanced using weights or machining adjustments to prevent vibrations during high-speed operation. Each stator winding undergoes insulation testing to ensure resistance to electrical leakage, essential for safety and durability. Some motors receive a varnish dip to improve insulation, provide thermal stability, and reduce the risk of coil loosening. The stator core is tested for proper magnetic conductivity and to check for any misalignment in the lamination stack. The rotor is carefully placed inside the stator, ensuring a precise air gap between them for efficient magnetic induction. A fan is attached to the rotor or motor frame to help dissipate heat, especially important in high-power applications. The motor housing, often made from cast iron or aluminum, is assembled to provide a stable frame and protect the internal components. End shields are installed at each end of the motor, securing the rotor and protecting the bearings from dust and moisture. The three stator windings are connected to create a three-phase system, typically in a star or delta configuration. A terminal box is added for easy connection to external power sources, often with labeled terminals to simplify installation. Grounding points are added to ensure safe operation, allowing stray currents to dissipate and preventing electrical shock. The exterior of the motor housing is coated with paint or a powder coating to prevent rust and provide durability. Seals are added to protect the motor from dust, moisture, and other contaminants, which is critical for motors used in harsh environments. The motor undergoes thermal testing to verify that it operates within safe temperature limits during various load conditions. Vibration levels are measured to ensure the motor runs smoothly and that the rotor is balanced correctly. Motors are tested for noise levels, as excessive noise can indicate mechanical issues or imbalanced components. Motors are put through a series of performance tests, including torque, power, and efficiency measurements, to ensure they meet specifications. A thorough inspection checks every component for quality and adherence to design specifications before final packaging. Japanese motors often comply with stringent industry standards, such as IEC or JIS, to ensure safety, efficiency, and quality. Motors are carefully packaged with cushioning materials to prevent damage during transport and maintain factory calibration.